My introduction to Chapter 18 on carboxylic acids is about soap. One of the earliest accounts of soap making comes from Pliny, the Roman historian who lived in the 1st century AD, who described soap being made from goat tallow and causticized wood ashes. He also wrote of common salt being added to make the soap hard. In the ruins of Pompeii, which was buried by the eruption of Mount Vesuvius in 79 AD, there was a soap factory, complete with finished bars. The goat tallow referred to by Pliny is rendered fat from a goat, and causticized wood ashes are ashes that have been processed with limestone, giving a mixture that's high in potassium hydroxide and potassium carbonate. In the American colonies, soap was made from wood ash lye and rendered fat from butchered animals, and usually done in the late fall when the weather was cool. The lye was made by placing wood ashes in a large funnel-shaped wooden hopper set over a bucket. The hopper was filled with ashes, and water was poured over the ashes periodically. Lye drips into a collection vessel beneath the hopper. Fat from butchered animals was rendered, a process that separates and removes all of the meat tissues that remain in the fat sections cut from animals. The fat cuttings are placed in a cooking vessel with water over an open fire because it's a rather stinky process. The mixture is boiled until the fat melts. The kettle is removed from the fire, more water is added, and it's allowed to sit overnight. By the next day, the fat is solidified and floated to the top, forming a layer of clean fat, or rendered fat. Then the soap can be made. Again, this is typically done outdoors over an open fire. The rendered fat's mixed with some of the lye solution in a kettle and boiled until the soap formed, a process that could take 6 to 8 hours depending on the strength of the lye. When the fire is put out and the soap mixture is allowed to cool, the next day reveals a brown jelly-like substance that feels slippery to the touch, makes foam when mixed with water, and it cleans. The soft soap was typically then poured into a wooden barrel and ladled out with a wooden dipper when needed. Hard soap could be made by adding salt at the end of the boil, but depending upon where you lived in the colonies, salt was expensive, so it was reserved for seasoning and preserving foods, and so they got by with the soft soap. When the rendered fats boiled with lye, a reaction like the one shown here was occurring. Fats, whether from animals or plants, are esters of 1,2,3-propane triol, commonly called glycerol. It's one of the products of the reaction, shown here. And fatty acids, carboxylic acids consisting of long chains of carbon atoms. So if you look closely here, there are these long carbon chains in each of these 3 groups that are attached to this structure, which is the fat that we begin with. This structure you've shown here isn't an actual fat. It's actually a composite used to illustrate the different types of fatty acids that are attached. These long carbon chains are mostly saturated in fats from animals, mostly unsaturated in fats from plants or fish. In this structure, the fat here at the top is a saturated fat, would be the kind of chain you would find in animal fats. The one in the middle is a monounsaturated fat. It's very common in plants. Things like olive oils are very high in monounsaturated fats. And then this last one with the 2 double bonds is kind of generically called a polyunsaturated fat. And these would come from fish or nuts and some other places like that. Regardless of the source, cooking the fat with strong base, in this example just sodium hydroxide, which is largely what lye is, converts it into a mixture of glycerol and carboxylate salts of the fatty acids. So this is the glycerol portion, and then these are the carboxylate salts of the fatty acids. This is soap. Soap's cleaning power comes from the curious properties of these fatty acid carboxylate salts. The carboxylate groups are hydrophilic, meaning water-loving. So this end of the molecule interacts with water very, very strongly. And it tends to confer a certain amount of water solubility. But the long hydrocarbon chains, so these ends of the molecules, are lipophilic, meaning fat-loving, and they tend to associate with other hydrocarbon chains. These kinds of compounds that are both hydrophilic and lipophilic are called amphiphilic, meaning having both properties within the same molecule. When mixed with water, this amphiphilicity results in the formation of aggregates called micelles. One of those is pictured here. This is a micelle. These are space-filling models of fatty acid salts that we see here. In typical soap, each micelle is a composite of anywhere from 50 to 100 molecules, with the hydrocarbon tails clustered together in the middle. So if we look deep down inside here, these are the hydrocarbon tails kind of pointing toward the middle of all of this structure. And the polar carboxylate groups here on the outside. Soapy water that contains these micelles removes grease by breaking it into small particles and enclosing the grease in the middle of the micelle, in the hydrocarbon interior. And then when you rinse the soap away, these micelles containing the little particles of grease go with it. And that's how soap works. So that's our introduction to carboxylic acids. And here's your usual list of study problems that I recommend that you work on. Carboxylic acids were some of the first organic compounds to be isolated and named. In fact, the names of many organic compounds are derived from a related carboxylic acid. Benzene, for example, gets its name from benzoic acid and not the other way around. As a result of this, IUPAC has accepted a large number of these names as acceptable alternatives to the systematic ones. Another curious feature of these names is that they typically refer to a particular source or a characteristic of the compounds. Formic acid, for instance, gets its name from the Latin word for ant, and it can be isolated from many species of ants because they produce it in fairly large quantities as a chemical defense mechanism. Acetic acid gets its name from vinegar, and it is the substance that's responsible for the sour flavor and aroma of all vinegars. Butyric acid, curiously, gets its name from butter. Although in this case it turns out it's the compound that's responsible for the unpleasant smell of rancid butter. It's actually part of a fat that's present in fresh butter, and when that fat is broken down, butyric acid is released, and it has a very displeasing aroma. Caproic acid gets its name from goats, and it turns out it is responsible for their rather peculiar smell. If you've ever been near a goat farm, it has a very unusual smell. And it's also akin to the unpleasant smell of dirty sweat socks. Stearic acid, shown here, is commonly found in beef fat, also known as tallow, and its name comes from the Greek word for tallow. Linoleic acid, which we see here, which is a polyunsaturated fat, it has two double bonds in it, is found in many vegetable oils, and in fact its name comes from the Greek word for flax, which is a plant that we get a lot of oil from. Flaxseed oil is a very commonly used oil. It belongs to one of two families of so-called essential fatty acids that are fatty acids that humans and other animals must ingest because our bodies require them for good health, but our bodies cannot synthesize them. A diet deficient in linoleic acid, for instance, usually results in symptoms of skin scaling, hair loss, and poor wound healing. Our bodies do produce a wide variety of carboxylic acids. One of the more curious classes of carboxylic acids are the compounds you see here. Here's the carboxylic acid group. This is known as PGE1. It is a prostaglandin. The name prostaglandins comes from the prostate gland, where they were first isolated in the 1930s, and they were thought to originate there. In fact, we've found out subsequently that very small amounts are produced in almost all of our organs and tissues. These molecules are locally acting messenger molecules that mediate everything from muscle contraction to platelet aggregation to cell growth to thermoregulation. Very important compounds indeed. This table, which you find in your text, lists both common and systematic names for a variety of important carboxylic acids. There are a couple important things to note here. For instance, if we look at lactic acid and mandelic acid, we can see in the systematic names that the alcohol groups are named as prefixes. That tells us that IUPAC prioritizes the carboxylic acid group over the alcohol, and so these are named as carboxylic acids with hydroxy substituents. The systematic name for oleic acid, we can see, so that's this compound here, and this is the systematic name, and you'll notice that it is an ene-oic acid. So the double bond is named with a prefix, or excuse me, a suffix, as is the carboxylic acid, and the double bond suffix comes before the carboxylic acid suffix. The next couple examples, the benzene carboxylic acid, benzoic acid, and salicylic acid, you'll notice it is orthohydroxybenzene carboxylic acid, illustrate how a carboxylic acid attached to a ring is named with the suffix carboxylic acid. And for compounds that contain two carboxylic acids, they're simply named as dioic acids. So malonic and succinic acid, for instance, are dioic acids in their systematic names. And for the exocyclic carboxylic acids we see in phthalic acid, you'll notice it's named as benzene dicarboxylic acid. Carboxylic acids are structurally similar to aldehydes and ketones with a trigonal planar geometry around the carbonyl carbon. Here we see the structure of formic acid, and the structure is drawn in its most stable conformation. Free rotation can occur around the carbon-oxygen single bond, but the most stable conformation is one where the oxygen-hydrogen bond is in fact eclipsing the carbonyl. So the whole structure, all 5 atoms in the structure are coplanar. Because they possess a carbonyl oxygen with its lone pair of electrons and a hydrogen bonded to oxygen, carboxyl groups can be both hydrogen bond donors and hydrogen bond acceptors. As a result of this, they readily form tightly hydrogen bonded dimers, shown here in a generic sense. You can have 2 carboxylic acid molecules interacting where we have a hydrogen bond donor, hydroxyl group from one, hydrogen bonded to the carbonyl of another, and then the hydroxyl group of that carboxylic acid donating its hydrogen to the carbonyl of the first carboxylic acid. We can see in our electrostatic potential maps here the complementary charges, positive charge in blue, negative charge in orange. Positive charge in blue, negative charge. This is a relatively tight interaction, and it's so strong, in fact, that for low molecular weight carboxylic acids, they even exist in these dimeric forms in the vapor phase. Acetic acid, for instance, exists largely as dimers, even as a vapor. Carboxylic acids are the most acidic class of compounds that contain carbon, hydrogen, and oxygen. They typically have pKa's in the range of 3 to 5, so here's just a generic carboxylic acid. Alcohols, aldehydes, and ketones are also compounds of carbon and hydrogen and oxygen, but they have correspondingly higher pKa's. They are correspondingly less acidic, and here are their corresponding acid-base reactions. There are 2 reasons for this level of acidity. One is the inductive effect of the carbonyl group. It stabilizes the negative charge in the carboxylate ion. So if we look at just one resonance form here, we have a negative charge here. We have the slightly positively charged carbon of the carbonyl, and it will inductively draw electron density away from that oxygen. The second reason is illustrated by this pair of resonance structures, where we can see that electron delocalization of this type results in the negative charge being shared equally by 2 oxygen atoms. Remember, our picture of bonding here is a hybrid of these 2, so the negative charge is distributed over these 2 oxygen atoms. In contrast, the conjugate base of an aldehyde or ketone while it is stabilized by resonance, we can draw these resonance structures, these are non-equivalent resonance forms. In one of these we have negative charge on carbon, and on the other we have negative charge on oxygen. Certainly negative charge on oxygen is more stable, it's more electronegative, but negative charge on carbon would be less stable. And so in composite, this structure is much less stable than that one, such that the pKa of this is much higher. As for an alcohol, its pKa is much higher because it's a localized charge, and it's not stabilized by induction or resonance. It's chiefly stabilized by solvation interaction with a solvent, because these reactions have to happen in some sort of solvent. Another way of illustrating the difference in the stability of an alcohol undergoing proton donation versus a carboxylic acid is illustrated here. So if we look at the change in free energy for deprotonation of ethanol, shown here on the left, so just simply deprotonating ethanol, forming the alkoxide and hydrogen ion, the change in free energy is 91 kilojoules per mole. So it requires a great deal of energy to remove the proton. And so that goes along with the pKa. By contrast, removal of a proton from something like acetic acid is a much lower delta G. It's correspondingly more acidic, and we can see the difference here. Again, this is entirely the result of the stabilizing effect of resonance and induction here, and the fact over here we have no internal stabilization. The only thing stabilizing the alkoxide ion would be solvation effects. While carboxylic acids certainly are more acidic than things like alcohols, they are not strong acids by any means. So if we just keep in mind here that acetic acid is, for instance, a weak acid, this number here corresponds to only a very small amount of ionization. A 10th molar solution of acetic acid in water, for instance, is only a little over 1% ionized. The carboxylate ion is stabilized by electron withdrawing groups. The inductive effect of electronegative atoms in close proximity to the carboxyl group increases the strength of the carboxylic acids by stabilizing the carboxylate ion. The strength of the effect depends on the electronegativity of the substituent and the number of sigma bonds between it and the carboxyl group. For instance, if we compare on the table on the right, if we look at the entry here for alpha chloroacetic acid, alpha fluoroacetic acid, alpha bromoacetic acid, alpha iodo, we can see that all of these are substantially more acidic than acetic acid itself. So the electronegativity of the halogen is drawing electron density away from the carboxylate ion, stabilizing the carboxylate ion, and we're getting correspondingly higher acidity, lower pKa. The effect is additive, so if one chlorine gives us some stabilization, two chlorines gives us more, three chlorines even more. In fact, you get into this range, trichloroacetic acid, you're starting to talk about something that's acting like a strong acid. Same thing is true for trifluoroacetic acid. It's a through bond effect, so depending upon the proximity of the atom to the carboxyl group, the effect will be stronger or weaker. So for instance, here on the left-hand side, here as reference, we have butyric acid. Its pKa is 4.81. Go all the way down to the bottom. This is the alpha chloro, the chlorine on the alpha carbon, and its pKa is about 100 times, it shows us is about 100 times more acidic. If you move the chlorine, this is what we would call beta chloro butyric acid, it still has a measurable effect, but it's dropped off precipitously. And even moving it all the way out to the end of the chain, it has a measurable effect. So the electron withdrawing effect is giving a little bit of stabilization to the carboxylate ion, and so we're enhancing the acidity ever so slightly. This is more data that shows us the effect of substituents. In this table, we've included also the effect of alkyl substituents. So for instance, we have propanoic acid, 2-methylpropanoic acid, and so on. If we look at these numbers here, there's very little difference between these. And so the conclusion is that alkyl groups have very little effect. There's a slight decrease in acidity compared to acetic acid, but that's primarily a solvation effect. These things aren't as soluble in water as acetic acid is, and so their pKa's go up ever so slightly. The data here in the middle of the table, these are the alpha halo derivatives. I showed you those on the previous slide. At the bottom of the slide, we can see that it's not just halogens, that other electron attracting groups like alkoxy groups and nitriles and nitro groups have electron withdrawing effects, inductive effects that stabilize the carboxyls. Depending on the strength of that inductive effect, we see an enhancement of the acidity relative to acetic acid, which is our reference on here. Our last look at structural aspects of acidity is that of benzoic acids, substituted benzoic acids. They're similar to aliphatic acids. What we see is that electron withdrawing groups, things like nitro groups, for instance, have the strongest effect, and proximity is really the key. The closer the substituent is, if it's, for instance, attached to an ortho, meta, or para, the closer it is to the carboxyl, the greater the effect. So if we look at nitrobenzoic acid, it's most acidic if the nitro is ortho, and then the acidity drops off quite a bit. There's virtually no difference between meta and para. And we see the same effect with other groups like fluoro, for instance. The greatest effect is when it's ortho, and it drops off substantially when it's meta and para. And that concludes our first part of Chapter 18.